All right. So binary lifting and Euler tool is what we are going to cover. So let me first give you the points that I am going to cover on a broader perspective. So first we'll try to solve a question, which is print kth ancestor, kth parent of a node. I hope that you guys are familiar with what is node and what is parent and what is ancestor, right? I introduced you into the first class only, right? Can I get a yes if you guys know what parent and ancestors are in a tree, right? All right. And then this will be a easy one. We'll try to solve this without using any trick or like just DFS only. And then this is what uh, this is the question that will introduce the need of something known as binary lifting, right? So then from this question, I will try to give you an intuition of binary lifting, right? Then we will solve the same problem, this problem, using binary lifting, and we'll get, eventually we can solve it without using binary lifting, but we will be end up getting TLE, right? So in this, we won't be getting TLE. So if we use binary lifting, then we will solve LCA. The like some of you were saying that LCA is what we are going to do with binary lifting. So this is what you were saying, that we will be finding LCA using binary lifting, but remember it uses this concept, right? Okay, I'll teach you, don't worry. And then we will be going through Euler tour, and also known as tree flattening. And as far as I have studied, we have two types of it. Like this is not a generic type, but yeah, we define it by these two types. And then we will be also finding LCA using Euler tool, right? So earlier I was planning that this class will be only of binary lifting and the next class will be of Euler tour, but I thought that it would be great to combine these two and then solve only problems in next class, like high level problems, 1800, 1900, 2018, right? So that is what my modified plan is. So are we all good to go to move ahead? Excited? I would say it is a very brilliant topic. If you see the beauty of, you will see the beauty of bit manipulation in this, and your mind will just go blown. I after studying this topic, I always wanted to teach, and today is that day. So I'm very happy. So if you guys don't know me, I am Dev Karan, expert on Code Forces and 5-star coder on CodeChef. So let's begin the class. Today is what? 26th of May. Okay, we have a issue. Let me just give me a moment. Just give me a moment. Now I think, yeah, it is fine. Fine. So what I was saying is, first we will initially solve a very simple problem, right? It can be solved without any technique. And the question is print the kth parent of a node, right? So I'll give you a tree, for example. So this is 1, this is 2, this is 3, and this is 4, 5, 6, and 7, 8, 9, right? Fine. So I want you to say that, okay, you will be given K. So K is 2 and a node will be given to you whose key is 7, right? So I want you to get the second parent of 7. Where is 7? Here is 7. This is the first parent and this is the second parent. So your output for this test case should have been 3, right? So, and you have to, of course, n is 1e5, which means that you just have to do a brute force. Come on, can you guys give me the brute force for this? It's easy, I think. Brute force is too simple. Yeah, we will maintain something known as a parent array while doing the BFS, and then we can normally use a while loop and then do our stuff to get the answer. Got it, everybody? What I said? Yeah, we will be storing something in parent and then we will be moving upwards, like its parent is this and its parent is this, and we will be doing it k number of times, right? So we are just motive is to do a DFS, sorry, and get a parent array. So let me draw the parent array. I won't be writing code for this because it is a problem to introduce binary lifting, right? It is not a very great problem. I would say it is a very cakewalk problem, right? So the parent array will look something. Oh, what is this, man? Right. So parent array will look something like this. Suppose this is 1, 2, 3, 4, 5, 6, 7, 8, and 9. And I think we require 9 only. So this is nothing, right? Ignore this. So whose one's parent is 0? I generally take any arbitrary node as 0 because I generally use one based indexing for our trees. Now 2's parent is 1, 3's parent is 1, 4's parent is 1, 5's parent is 3, 6 parent is 3, 7 parent and 8 and 9. All these parents are 6, right? So this is the array that you will be getting after doing a BFS. If I have the code, I'll show you as well. Right. So this will be the BFS DFS code, right? And what you are going, P of node is equal to parent, and this is how you can get a parent and everything. This is what normal BFS loop is, and this is what you just have to include it, and you will be having a P array looking something like this for this tree. Right now, what you will do, you have node as 7, right? You have node as 7. What you will do, you will run the loop k times. So you will either do a while k minus minus. This will run the loop k times, and what you will say that, okay, node is equal to parent of node. You will be doing a jump, and at the end you will return the node, right? If it is a return type answer, right? So now let's do a dry run for this. Initially node is 7. I'm over here, right? I'll run the loop 2 times. The first time loop will be running, we will be saying that, okay, node which was initially 7 is going to be parent of node. What is parent of node? 6, right? So now my node is 6, and I have run the loop once, right? Which means that this is my node now, and I just have to run the loop once more, right? Because k was 2. Now we are at this node at node 6, right? Who is node 6 parent? 6's parent is 3. So I will be moving over here, and this, after k becomes 0, my while loop will break and I'll return the node. What is at node 3, right? And what is our output? 3. So which is correct. Got it? It was pretty simple. I think I over explained, but anyways, got it, everybody? Yes. Okay, so shall we move forward? So now what are we going to do? We are going to modify this question, or maybe update this question, right? So okay, before that, let's discuss the time complexity of this. What is going to be the time complexity of this problem? Time complexity, order of n for DFS, and then order of k, which is again order of n, right? Approximately, right? And if n is 25, then it should pass, right? Yeah, e plus v is almost n, right? And that is what I wrote, order of n plus order of k, which is approx order of n, right? And it should pass if n is 1e, it should pass in 1 second. Now what I'm modifying the question is, you will be given q queries given, right? Each query will be having 2 integers, one is node and one is k. This is repeating q times, and you have to do the above thing for each of the query. So if you try to apply the above approach, what is going to be your time complexity? Your TC is going to be, first you will be doing an order of n DFS to get the parent array, and then you will be doing q times order of k, and also q is 1e5 and k is of order of n, which is 1e5, which means that it is going to give you TLE, right? Everybody agree? It is going to give you a TLE, right? Q is 1e5. This is 1e5. 1e5 into 1e5, 1e10. Can this pass in 100 seconds? Can this pass in 1 second? No, it can't, right? So it will give you a TLE. Now our work is to eliminate this. How can we eliminate that? Now this, so what will be the solution to eliminate the TLE? So this is where something known as binary lifting comes into the picture. And before that, before binary lifting, I would like to say something about intuition of binary lifting. Intuition of binary lifting. So I'll state a very random word, random statement. Suppose k is an integer. K is an integer. If we try to talk about bits, this can be written as sum of power of 2's. You guys agree? Every integer in this whole damn world, we can break it in sums of 2, right? This is what bits is about, all about, right? For example, if I say that, okay, I'll take an example of k is equal to 11. K is equal to 11 is what? 1 plus 2 plus 8, which is what? 2 power 0 plus 2 power 1 plus 2 power 3. And if we try to write the bit form of this, then what will it look like? This is 0, 1, then 1. This is what it will look like. So 0, 1, 2, and 3, 2 power 3, 2 power 1, and 2 power 0. Agree? This is the bit format of 11, right? Got it? Understood till now? What I said is true, right? This is 100% true. Everybody know this. Okay, let's move on to the this is the most basic thing behind binary lifting. Let's see what lies ahead then. Initially, what we were doing, we had a node, and we have some nodes, right? We have to find, let's number these. Initially, we were given a node and we were given some k. Suppose this is the kth parent of this node 1. So what we were doing is, we were doing a one jump, singular jump. We are going to immediate parent. And that is where we were lacking, right? What I can say that, if suppose I somehow store parents in powers of 2, what I mean to say is, suppose this is a node. For this node, and suppose n is 1e5. For this node, I store first parent, I store second parent, I store fourth parent, I store eighth, and so on up till 2 to the power x, xth parent, right? So how will this help me? Suppose if you want to get k equal to 11, right? K is equal to 11, which means, or we already told that, okay, 8 plus 2 plus 1, right? From the current node, we can go to 8th parent, which is stored already, right? Then from this node, we can go to its second parent. And from this node, we can go to its first parent. So this is first parent, this is second parent, and this is 8th parent, right? If we can do that, initially we were doing it in 11 steps, and now we are doing it in only 3 steps. And this is, I think, a very great improvement. And what is 3 approximately? Basically, let's leave it. Did you guys get it? Why did I try to store the parents in power of 2's? Yes or no? Anything like, no, you can also write no. You don't have to write yes. If you did not understand it, you can write no. I will make you explain again. Man, this is a big problem. Yeah, I'll repeat, don't worry. But somehow I am again signed out of Zoom. Okay, anyways, we'll continue the class. Yeah, so what I was saying is, initially, this is suppose node 1, or this is my given node, right? Initially, in order to find 11th node, let me draw in this fashion. Let me draw all 11 nodes. Just want to make it damn clear. It's not that hard, I will say, right? Just try to understand it, and it's a cakewalk. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? Let's connect these all. Suppose this is a tree, like a branch of tree, I would say. and you have to find 11th node of this. This is the node given to you. So what will you do? Okay, then go to, what will you do initially, like with the parent trick? First you'll go to this, then you'll go to this, then you'll go to this, then you'll go to this, 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 and this, right? So it is going to take you an order of n time, linear time, right? Now what I'm saying is, suppose 11 can be broken down into 8 plus 2 plus 1, right? So if some, and what are these? 8, 2, 1, powers of 2s, right? So if for every node I have um, power of 2's parent, right? Which means that, okay, for this node, I have 2 to power 0, which is first parent, 2 to power 1, which is second parent, 2 to power 2, which is fourth parent, 2 to power 3, which is eighth parent, and so on. For every node I have this. Then what I can say, I can do it in a very short time. How? Let me explain you. Okay, I should not erase this. Let me explain you. All right. So this is your node. First, you will break down this k, right? K has initially k was 11 and it is 8 plus 2 plus 1. So if I jump to 8th parent of this node, like this part will be clear, this part will be clear. So let's jump to the 8th parent. 1, 2, 3, 4, 5, 6, 7, 8. Let's jump to 8. I don't know. 1, 2, 3, 4, 5, 6, 7, 8. Okay, this. Let's jump to this. Okay, I have to draw one more node, right? Right, which means that, and it will be already stored, right? 2 to the power 3, 8th parent will already be stored. So in one jump, you can go from here to here. Now you will say that, okay, 2 to 8 is covered, 2 to the power 3 is covered. Now I just have to cover 2 to the power 1 from here. So first parent and second parent, I'll go to here. And then I just have to do one more jump here. In how many steps were you able to reach the required node? 3. And initially, using brute force, you were doing these steps. And how many steps were these? These were 11 steps, right? Which means that this is a massive improvement over previous approach. Now, did you guys get it? Yes or no from anyone? Right? I think it made very clear, right? So, okay. So don't you think that the number of terms in the sum of k as power of 2's will be the number of jumps? Am I clear? What I said, I'll repeat. Listen carefully. The number of terms in the basically expression of denoting k as a power of 2's will be the number of jumps, right? Yeah, we'll do that. Don't worry. We'll do a dry run of third. Okay, you want to my answer? If my answer is third node, then how will I find? Okay, if you want to find 3, break it in power of 2's. Like if you want to find the third parent, break it in power of 2's, which is 2 plus 1, right? From here you will, so this is 2 power 1 and this is 2 power 0. 2 power 1th parent will be stored for every node. 2 power 0th parent will also be stored for every node. 2 power 1 parent will be stored for every node as well, right? So you will be storing all the power of 2's parent for every node, right? So you can jump from 2 power 1th parent and then to its 2 power 0th parent, right? So okay, you got it. Fine. So how many terms are there? If I try to write 11 as sums of power of 2's, we will be having 3 terms. And if we have 3 terms, which means that we will be requiring 3 jumps. So what is this 3? How are we getting this number 3? But for each node, we have to calculate all the parents. Then what is the use? We'll go to it. We'll have to find a relation. Don't worry, don't rush up. Just try to understand what I'm trying to say, right? So k is initially 11, right? And initially we were doing it in 11 jumps, right? Now what we are doing in 3 jumps. And how are we getting the number of 3? Basically log of k, right? So initially my time complexity was order of n, order of k. Now for per query, now I am able to use this fact, this any integer can be written as sum of var of 2's. I was able to do each query in order of log k. We just have to do some storage and I will be able to do that. Do you guys agree? Just forget about the storage as of now. How are we going to do that? We'll do that, don't worry. But if you are given the storage, don't you think that you will be able to do this massive optimization, right? Okay, I think everybody agrees. Now let's talk about how let's talk about the storage. How are we going to do the storage, right? So before that, I would like to raise a simple question. How many parent per node will be stored? How many parents per node will be stored? If we, yeah, exactly, log n, exactly. Do I have to explain it? No, not n. It would be log n. Suppose you will be storing 2 to the power 0 parent, 2 power 1 parent, 2 power 2 parent, 2 power 3 parent, and suppose you will be storing up till 2 power 17th parent. This crosses 10 to the power 5, and we only have 10 to the power 5 nodes in the worst case, right? So we just have to store 17 parents. We just have to store 17 parents, right? So this will be stored, this will be stored, this will be stored till here, right? Which means that per node we will be storing 17 parents. Yeah, 17 is the number. So how will my parent array will look like? It will be of definitely a 2-dimensional array. So let's call it parent. The first term will be the index of the node, for which node we are going to find the 2 to the power xth parent, right? So node, and over here you will be having x, right? X. And what does this parent will denote? Parent node x will denote 2 to the power xth parent of node. Is this thing clear? This is my array. Parent is the name. Node is the basically, you guys know. Is this clear or not? Yes or no? This is how I am going to use a data structure to store, right? Okay. 2 to the power xth parent of node. Now what I have to say, okay, what is the maximum limit of x? We already discussed x is up till 17 and node is up till 2 to the power, 10 to the power 5. So what can be the space this array requires? 10 to power 5 into 17, agree? Which is what? Approx n log n space. Approx n log n space, right? N log n space is what this array going to require, which is, I think, okay. It won't give any space limit exceed, right? So we are checking this tick as well. Okay. Now, I just want to ask, till now, is there any doubt? Because we are going to do the transition now, right? How are we going to store, basically get the data? So that is a basically most important part of this binary lifting. So till now, everything is completely in your mind or not? I just want to ask that. If you have any doubt, just go ahead and straight away ask. No doubts? Okay, how many do we have in the class? Okay, we still have to win. Brilliant. Okay, sit back, relax. This is the most important and most craziest thing in binary lifting. I just love this thing. See, I'm going to draw some things. So suppose this is a node. This is another node. And this is another node. Suppose node 2 is node 1's 2 to the power x minus 1th parent, right? Suppose this is, and node 2 is 2 to the power x minus 1th parent. Node 3 is 2 to the power x minus 1th parent of node 2, right? Got it? So what will be the relation between these two? What will be node 3 of node 1? Can I say that it is 2 to the power nothing but 2 to the power xth parent? Got it? We just add these things. So don't get confused. This is not a regular edge. This is an imaginary edge. they won't be connected in this way, but yeah, they like there will be some nodes in between, and we are just skipping those nodes, right? 2 to the power x minus 1th parent of node 1 is node 2, and 2 to the power x minus 1th parent of node 2 is node 3. So we just discovered that okay, the 2 to the power xth parent of node 1 is going to be node 3. This is very simple thing, right? No issues on this. All right, now I'll write some simple facts. I'll write some simple facts. Parent of node 1 x minus 1 is equal to node 2. Parent of node 2 x minus 1 is equal to node 3. And one more thing, parent of node 1 x is equal to node 3. Got it? So these are the three statements. You can just see the graph and write it on yourself, right? Right, this is simple, right? These three are no-brainer. Everybody on the same page? Like, do you guys know how am I writing these? Right, I'm using this thing, this highlighted thing, and this graph as well, right? So these are the three statements that I wrote. Now I'll do something. I'll use the two of these. So the bottom one states that parent of node 1 x is equal to node 3. And what is node 3? Can I write this? This is node 3, and can I write this instead of this? Parent of node 2 x minus 1. Agree how this thing came using the last two statements? Because these two were equal, so I just equated these two, right? Now I am going to say that okay, node 2 can be replaced by this thing from here to here, right? So let's do that. Parent node 1 x is equal to parent. What is node 2? Parent node 1 x minus 1. Okay, I have to shorten this thing up. Parent node 1 x is equal to parent of parent node 1 x minus 1 x minus 1. Is this statement clear or not? Is this equation clear or not? I just draw a graph using this thing, which is how you are going to store the data. I wrote three simple statements, and using these three simple statements, I first got to this statement, and then from this I got to this. Now I am asking you, is this thing clear? Is this statement, how we got this, is clear or not? If this is clear, binary rifting is yours. Everybody, I don't want any single person to say yes. If you guys just write anything, if you are listening to me, just write yes or no. Okay, I think it is clear to everybody. Okay, fine. Don't you think that okay, let's write this node 1 as node only, because only singular node is being used, which means that if you are given a node and you have how can I say that? Okay, so this is the DP relation, if you say, don't you think? From if you have the x minus 1th level, then you can have the xth level using a relation, right? Got this? If you have x minus 1th level, you can have xth level. And what is the base case of this relation? You always know this thing, don't you know? You always know what is this, don't you? You guys know 2 power 0 is what? 1. So first parent of every node is known to you, don't you think? Right? So if parent of node 0 is known, then parent of node 1 can be calculated using this. And if this is known, parent of node 2 can be calculated from this, and if this is known, parent of node 3 can be calculated, and so on. We can calculate till to parent node 17, which is the maximum thing required, right? Which means that we can make a bottom to up DP, and we can fill the DP using bottom to up approach, and eventually we will be able to fill our whole table. Don't you guys think? Was I able to make you understand how is this thing useful? We knew this, everybody knew this, everybody knows this, right? Given a tree, you can use a simple DFS and just know this. From this you can get this, you have the equation. From this you can get this, you have the equation. Which means that from x minus 1 you can get x. So you can, if you know one of them, you will know all of them using this equation, right? Isn't it beautiful? Now I'll just write a code. I think I have explained everything about binary lifting. Just we have to combine all these things in code, and you will see the beauty of binary lifting. Guys, can you give me 2 minutes? I will be back in 2 minutes, right? Please give me 2 minutes. Just try to absorb this thing once more, and just give me 2 minutes. I'll be back. All right, I'm back. क्या हो रहा है chat में? Anyone supporting है भाई? All right, I think you guys went through this. Okay, so I think I have explained everything related to binary lifting. Just we'll now move on to the code part, right? So is this screen visible? Is this text editor visible? Sublime text. Fine. What about the font? Should I reduce the font? Increase the font, sorry. Or is it clear? How about now? Okay. Right. So you just have to find. So all right. So what was the main problem statement? If you go through the main problem statement, we were given a tree, of course. We were given a tree, and then we were given Q query. So I'll just take the input in a very formal way. So I'll be given n. Got it? Now I'll be given n minus 1 edges, right? So I'm just creating a vector over a tree over here, nothing else. U and V will be given. U V adjacency of U dot PB V. PB is pushback. Adjacency of V dot pushback U. Right now I will be given a Q. And while Q minus minus, I have to just print I will be given node and k and print kth parent of node. So this is the main thing. Now just I have to do some pre-computations. So I will be requiring that parent thing, right? So okay, wait. Um, all right, I will draw a vector int parent, or I guess clear that this thing is nothing but dp. This array is bdp, right? This parent, I can write it dp. This whole, the whole binary lifting is dp, nothing else, right? We found a relation. This is the dp relation. This is the transition, how transition are being done, right? This is only dp. So I will name this vector dp. The size is going to be n plus 1 dimension, and the other dimension is going to be 17, right? And how will I initialize? Let's initialize with 0. 0 is the null node in my case, right? This is how I do the things. Now, okay, this thing is created. Now I just have to fill it, right? So how can I fill it? So of course, we will be doing a traversal, and the traversal that I prefer is DFS, right? How we do node parent adjacency, this thing that we calculated by reference. Don't forget that. All right. Now over here, we know something, right? We know node's first parent, immediate parent is par, right? So let's do that now. So dp of node 0 is par, right? And then now it's time to explain you some satisfying things. So suppose, let me draw a very large random tree. Just bear with me. I have to draw this tree. All right. Suppose we are over here, right? This is node, this is our parent. Now, if we are over here, which means that we have already encountered it's this node's DFS and this node's DFS, right? So don't you think that before, like before going to this node, we should have calculated everything for this node, right? Because when we were at here, we should have calculated everything for this. When we were at here, we should have calculated everything for this, right? Because like the data will be stored in the upward fashion, right? And if I say that, okay, if I'm over here, everything for above nodes are calculated, then we can calculate for this thing as well, right? So that is what I'm doing. Before going to the DFS of the next node, what I'm going to do is do a simple for loop for int I is equal to 1, I less than equal to 16, I plus plus. And what is this 16? This is approximate. This is nothing but log n, approximate log n, right? N is 1 for 5. Now what we have to do? We have this relation, right? We have this relation. We are going to use this only. So let's use this now. Right. Okay. So let's use this. So dp of node x. So dp of what is x over here? X is nothing but I is equal to dp of node I minus 1, I minus 1. This is nothing but the relation that we got. And see, dp, suppose I is 1. So dp of node 1 is equal to dp of, this will be dp of node I minus 1, 1 minus 1 is 0. So this is already known. So this is already known and it is one step up, right? Which means that we are writing something as node I is equal to dp of there will be another node 2. Let's name it. What is node 2? Node 2 will be the immediate parent of DP of node 1 and I minus 1. And node 2 is definitely above node, which means that, okay, suppose this is node and this is node 2. And everything for node 2 is already calculated, right? Everything for node 2 is already calculated. So this will again give this a value, right? Okay, don't worry, I'll do a dry run, but I was just trying to satisfy you with this writing code. Don't worry, you will get better with it. But this is how the transition is going to be. Are you guys like clear with this? Or I know it is difficult to grasp, but anybody got any idea what this loop is doing? Of course, we are using this DP relation and using this 16 times to just calculate it. But I know that you should not be, it should not be too much satisfying for you as of now. So don't worry, I'll do a dry run and it should be then, right? So first we calculated everything for a particular node and then we'll do a DFS. So what is left in DFS? Auto IT in adjacency of node. This is very Nova is thing. So if IT is parent, then continue. And if it is not, then transfer the DFS to its child. So node become IT, parent become node, adjacency and DP, right? And this is how you will be calculating the whole DP table, this DP table, right? And after that, after this DP table is generated, right? For each node, you have 17 parents, starting from 2 power 0, 2 power 1, 2 power 2, up till 2 power 17, 2 power 16, sorry, right? Now from using this, you just have to print the kth parent. Now tell me, if you have the DP table, if you don't understand it, just don't leave the class. Try to stay with me. I'll give you a dry run example and then everything will be clear, right? Just bear with me for 10 more minutes. All right. Now, okay, let's do one thing. Let's first of all calculate the DP thing, and then we will calculate the how are we going to get the kth parent from the table, right? So let me draw a tree for you, a random tree. So this is 1, 2, 3, 4, 5, 6, and 7. So we have 7. What is log 7? I think let's keep it 3. Let's have it as 3. Right. So we will be having a table with 7 rows and 17 columns, I think. So 1, 2, 3, 4, 5, 6, and one more. Okay, let's do one thing. No, that should. All right. And these are the columns. This is 0, 1, 2, 3, and 4, and so on. We won't be requiring beyond 2 power 8 or maybe beyond 2 power anything. 2 power 2 will be hardly required, right? And so on, right? So suppose what this 1 0 signifies, it signifies that, okay, once immediate parent is what, right? So what are we going to do? We are just going to follow this loop, right? This loop. Is my cursor visible? This complete loop. So how we are going to start the DFS? We are going to start the DFS. Okay, I forgot to start the DFS over here. So we will be starting DFS. What will be the node? 1 will be the node that will be starting. Parent will be any arbitrary node. I generally take it as 0. You are free to use any other number, not in the range of n. Adjacency and then DP, right? And after this, we will at line number 79, we will be having everything of that node. So okay, we will be starting with this. So let's start in our dry run as well, right? So what is our first line doing? My first line is saying that, okay, DP of node 0 is parent. So DP, what is node? Node is 1, right? So DP of, it is saying that DP of 1 0 is parent is 0. So let's do this, right? Then what it is saying that, okay, from 1 to 16, I am going to run a loop. So let's do it for 1. 1 says that, okay, what will be the relation be? dp of node, what is node 1 and what is I is 1, is equal to dp of 1 I minus 1 I minus 1, right? What is this? This is 0, and of course 0 will be there, but it will be initialized with 0. The whole array will be initialized with 0. So we are saying that, okay, dp of 0 is 1 1, and what is dp of 1 1? Basically second parent of 1, second parent of 1, right? dp of 1 1 is nothing but second parent of 1. And do we have a second parent of 1? We don't have the first parent, right? So we'll say that, okay, second parent of 1 is any arbitrary node. So don't you think that it should be 0? Now from this, if you see that, okay, as I is increasing, my answer will be shifted towards the higher level, and dp of 1 1 don't exist, so dp of 1 2 also don't exist, right? So it is wise to like just do a 0 to everything. Got it? How did I fill this thing? What is 0? 0 is nothing but a arbitrary node, right? Got it, guys? Anything? Yes, no? Okay, seems like everybody left the class. Or what? Got it now? It's simple, I think, right? We just, this is 0 is a garbage value. If we don't have the, it is possible that, okay, if I am, my node is 6, it is possible that we are demanding 2 to the power 10th parent of this. Do we have a 2 to the power 10th parent? No. So we'll just say that, okay, 0 we'll say that, okay, dp of 6 10 is 0. What does 0 signifies? 0 signifies that, okay, that is any arbitrary node, which means that it's that parent is not existent. That is what I did, right? So I did it for dp, or I did for 1. After doing that, I equal to 1 to 16 traversal, I'll go to 2, right? I'll go to 2, of course, because this is the dp movement, this is the dfs movement, sorry, right? So by dfs movement, I will be at 2. Now for 2, that same story will do again. So dp of 2 0 is what? dp of 2 0 is what? Its immediate parent, which is 1, right? So let's do it. Now I will use the relation dp of 2 1 is dp of 2 0 0, right? dp of 2 0 is what? 1, and dp of 1 0 is what? 0. And once 0 start coming, everything else will be 0, right? So this is how we filled the array for second. Now for second, dfs will be transferred to no one. Now the next dfs call will be made for 3. So let's do for 3. So we already know dp of 3 0 is 1. Let's do this, right? This is the most basic statement. And then the relation dp of 3 1 is equal to dp of 3 0 0. So which is, what is this? dp of this is 1, and dp of 1 0 is nothing but 0, does not exist, right? Which means that 0 0 0 0 0. And don't you think now my dfs will be going to 5, right? Now as my dfs goes to 5, we will be having something interesting. So dp of 5 0 is already known to us, which is 3. So let's do this. Now we'll go to the loop I equal to 1. So dp of 5 1, dp of 5 0 0. What is this? This is 3. So dp of 3 0 is what? 1, which means that, what is dp of 5 1? 2 power first parent of 5, which is second parent of 5. What is the second parent of 5? 1. And what did we stored? 1 only. Are you guys able to see the magic now? All right. So now if we use the relation for dp of 2, this is going to be dp of 5 comma 2. So dp of 5 1, and what is dp of 5 1? We just stored 1. dp 1 0 is 0. So it will start getting zeros from here. Now DFS will be transferred to what? 7. Now as the DFS is at 7, what we are going to do? DP of 70 is already known to us, which is 5. We'll do that, and then we'll use the relation that DP of 71 is equal to DP of 70 and 0. DP of what is DP of 70? This is 5, nothing but 5. So DP of 50, what is DP of 50? 3. So the second parent of 7 is 3, 1 and 2, right? And then if we do the relation for DP of 7, 2, it is going to be DP of 7, 1 and 0. Oh, sorry, 1. Right? So DP of 7, 1. What is DP of 7, 1? 3. And DP of 3, 1 is 0. So 0. And every time this thing will be above the particular level, right? So if you are at 7, this thing is going to be above this, right? Because this is a DP relation for this. This is a parent of this, and parent always lies above, right? So, and we are using a DFS, which means that this thing will always be calculated. This is damn sure, right? So DP of 3, 1 is 0, and we start getting 0. So everything is 0 now. And then the DFS call will be transferred to 6. So DP of 60 is known as 3. Let's do it. Then DP of 61 is equal to DP inside will be DP of 60, which is 3 and 0. Oh, sorry, 1. Oh, sorry, 0, 0 only. So DP of 30 is 1, and everything now will be 0 because fourth parent or 6 is not available, right? And obviously result has been given that, and we'll be giving that only. Just trying to save some time. And if you try to look at 4 as well, this, it will look something like this, right? And this is how, and everything up till 16 will be 0, right? So this is how your DP will look like. Let's try to confirm a bit of things. So let's say that, okay, DP of 7, 1 should be giving you second parent of 7. What is the second parent? 1, 2. Second parent of 7 is 3. What is DP of 1, 7? 3. So it is confirmed. You can confirm each and every relation, and this DP table will be giving you correct answer, right? And this is how we were able to do DFS, and at every node we will be having 16 extra loops, right? 16 extra loops. So 16 into n will be the time complexity of the DFS. So we will which is approximately order of n only, which means that we were able to compute this whole DP table in order of n only, right? And then you just have to do a run on queue, right? Now tell me, is it satisfying enough how this DP is calculated? Everybody, not only Rishi, everybody. I just want to ask everybody. N log n, yeah, n log n, sorry. Not n into 16, n log n. Sorry, my bad. I just ignored 16. I just took 16 as a constant number. My bad. And n log n will be the time complexity of the DFS, right? All right. So this is how my DP table will be stored. So this 10 lines or 7-line codes is doing the great stuff, right? Now, till now, here we have our DP table calculated, right? Now I just have to print the kth parent of node using this DP table, right? So how are we going to do that? That is our main question left now. Okay. Now find kth parent. This is too simple now. For 7th node, third parent, 3 parent. Okay, I think you are talking about example. For 7th node, 3 parent. Okay, the parents will be stored only in powers of 2s, right? The parent will be stored only in powers of 2s, and using this we can define any k. That is what we are doing. That is what we are trying to do. So just hold on, you will get your answer using set bits. Okay, yeah, we can do that. Yeah, actually that is what we should do. But I do have a different approach. Just I'll write the approach and tell me if it is correct or not. I will maintain a variable, something known as count, and then I'll say that, okay, while k exists, if k and 1 is true, node is parent, or maybe dp, dp of node cnt, and do a cnt plus plus, and k is equal to k right shift 1, and after this while loop just return the node. Tell me, what is cnt? Nothing but the bits, nothing but the bits, the bit number. Let's do a dry run for 11. Let's do a dry run for 11th parent, or maybe let's do a dry run for, let's try to find the 7th parent, third parent of 7, right? So k is 3 in this case. My count will be 0, right? K and 1, this is true, yes, because k will look like this and 1 will look like this, and is going to be 0 1, right? So and is 1, so we will be going inside this loop, right? So node is equal to dp of node comma count, which means that we just eliminated. So 3 is a combination of 2 plus 1. We just eliminated this 2, this 1, right? We just covered this thing. So now my node is going to be, initially it was 7, now it is going to be dp of 70, right? So dp of 70, what is dp of 70? 5. Now, and count is incremented to 1, because now we have computed for 2 power 0. Now we'll check for 2 power 1, right? And then k is k by 2, which is again 1, right? K is 1, and which means that now we just have to find the first parent of this. Now if this k is valid, if k and 1 node is equal to dp of node count, which is just 50, dp of 51, sorry, 51, because count is 1. So dp of 51 is 1. So my node become 1, count became 2, and k eventually became 0. We'll break out of the loop and we'll return node. We had to find third parent of 7. First parent, second parent, third parent. 1. What are we getting? 1. Tell me, easy or difficult? Interesting or boring? First tell me this, interesting or boring? Yeah, of course interesting. It's very interesting. And easy or difficult? How about easy or difficult? Okay. Hey, can you 11th parent? Okay, 11th parent does not exist, so it is going to be give you 0 only. Like, don't worry, I'll the last example. How can I, like, we will be just talking about zeros only. So 11th does not have any significance, but yeah, so I believe that third parent was the maximum that we can get. So that's why I did the maximum possible iteration. That one where you took 8 plus 2 plus. Okay, we'll try to do one thing. Just hold on a second. I'll try to draw an example if you want to. Okay, are you guys feeling difficulty in this code? The code that I wrote in white. Can simplify it. I can simplify it. It's too easy to simplify. If you are facing a difficulty for 11, just break it. 1101, I think it is the combination. 3210. Yeah, it is the combination. And then suppose you want to find, suppose just you have node you will start from the most significant bit. Whenever you find this as set, you will say that okay, node is equal to dp of क्या कर रहा हूं मैं, dp of node, and what you will be doing a reverse count from I equal to 29, I greater than equal to 0, I plus I minus minus. This will be the loop for most significant bit to least significant bit. And so node will be, if this is set, if the ith bit is set, do this, and every time ith bit is set, do keep on doing this, and at the end you will be add. So suppose if I try to do 3, so node is equal to dp of node 3, right? And then you will say that okay, dp of node 3 and 2, and then eventually you will just keep on doing that. So this is another easier way of doing this loop. Got it? What I did? I think it is, if you are comfortable with this white code, you can definitely go through it. And if you don't find it comfortable, then you can use that most significant to least significant bit thing, right? I have written this code in rough, and I will code that most significant to least significant bit, right? So both of the approaches gets clear. I think this will be the easier part. For int I is equal to 17, I greater than equal to, the most significant bit is 17 that I'm going to take, and I minus minus, and I think 16 should be the place, because 16 is the maximum index that you can access. So if k right shift I ended with 1, which means if this is set, then I'll say that okay, node is equal to dp of node and I. And I think this should be the thing. Let's try to solve this. Okay, this is okay. Let's write this tree only. How many nodes? 7 nodes. 7 nodes. Then 6 edges. 1 2 1 3 1 2 1 3 1 4 and 3 5 3 6 and then 5 7. Right, and then you will be having, suppose q is equal to 2, and 2 queries will be give me the third parent of 7 and give me let's say third parent, let's get 11th parent of 6 ka 11th parent. Let's see how is this getting calculated. Okay, okay, we did not got any answer. Where did we went wrong? Let me have a look. Live coding में यही दिक्कत होती है, sometimes code gets crashed. Okay, so we are able to calculate that dp vector. Something is wrong in our this while loop. int q while q minus minus. Okay,
The scene queue is missing.
oh, thank you. See, I think this is also working. Third parent of 7th is 1, which is what we are getting, and of course 11th parent of 6 is 0 because it does not exist, right? Okay, you guys started spamming scene queue in the chat. Sorry, I missed it. Anyways, is this thing clear? Like you are free to use any of the code, right? This code or this code to calculate the kth parent. I think this would be simpler. I am just realizing it, but anyways. Now tell me, any doubt related to binary rifting, how to find the kth parent in okay, the most important thing, what is the time complexity? Now, after we did binary rifting, order of n log n initially for DFS, then per test case log of k. So is this acceptable in, and overall it is going to be n log n plus q log n, or if you want to simplify, just write it in one word. Order of n log n is the time complexity of the problem. Now, tell me, were we able to eliminate the time limit exceeded verdict or not? Right? How was it? How was the binary lifting? Damn, cool. Was I able to simplify it for you guys? All right. Let's move on to the second problem. Okay, let's see the checklist once because we have around 48 minutes left, and I know that you guys want to see IPL as well. So I won't extend because I also want to see it. Anyways, so this is done. This is done. This is done, and this is also done. Right now we are going to discover LCA using binary lifting. Then if we'll see that if we are able to do the Euler tour in this class or not, right? जेई की कोचिंग की फील आ गई कैसे? Oh, nice. All right, so we want to do a LCA. So let's first draw a tree. Let me explain you what LCA is. Suppose this is my small tree and I want to say that, okay, LCA, what is LCA of 4,7? So where is 4? Here is 4, here is 7. So this is the LCA. So LCA of 4,7 is 2. How do you guys find LCA generally? The lowest common ancestor. See, this is 4, this is 7. The brute force is what I'm going to teach you now. From root, this is root. From root to one of the nodes. Let's say this is A, this is B. From root to A, write the path 1, 2, 4. From root to, or maybe write the reverse path from A to root. Write the path from A to root 4, 2, 1. Write the path from B to root 7, 5, 2, 1. And you will see that, okay, the path will start looking something similar at the end, right? So which is the lowest level? Which of them has the lowest level in the same looking path? 2, right? 2 has the lowest level. Like lowest means lowest in this direction, right? So 2 is the LCA. So this is the brute force method. You know how to do this path printing using this parent array, simple parent array, no binary lifting, right? And then the first similar node in path of both of the nodes is the LCA. So this is how you get it using a brute force method. Is it thing clear? Is this thing clear? Right? Simple, I think. All right. So the brute force is done. Now I just want to say that, okay, what is the time? I just want to ask, what is the time complexity of brute force? You just have to print 2 paths. First, you will write the parent array. How will you get the parent array? Order of n. You just have to write the 2 paths. So 2 times order of n again, right? And then comparing the paths. So again order of n. So summing everything up, it is going to be order of n only. So time complexity is order of n. Now again, I am a very bad person. What I do is I give queries. What will happen if I give you queries? You will get TLE, Q into n. Yes, TLE. And how will you eliminate TLE? Using binary lifting. Very simple. How are we going to use binary lifting to solve TLE? Just have to follow 2 steps, right? Step number 1 is bring them to the same level using binary lifting. And what is step 2? The step 2 is move A and B to every unequal nodes 16 to 0. This is very important. 16 to 0 is very important, right? So forget about step 2 as of now. We'll focus on step 1 first. What is step 1 saying? Bring them to the same level using binary lifting. So let's do this over here only. 4 is one of our nodes and 7 is one of our nodes, right? Are they on same level? Are they on same level? They are not on same level, right? Levels are like these. They are not same level. So let's try to bring them on same level. So what do you think? Is it easier to move the level up or move the level down? It is easier to move the level up because we might not have any nodes down, right? So let's move 7 up. How are you going to get the 7 up? Remember I taught you level thing, level, how to calculate the level. What is the level of this 0, level of this 1 1, level of this 2 2, level of this 3 3? You can use a simple DFS to calculate the level as well. And after calculating the level, what you can do is you can find the difference of levels of A and B, which is 1. And whosoever is at the greater level, you can say that, okay, move this node, find, or maybe find the kth what is k? K is the difference. So k is 1, find the kth parent of 7. How can you do that? We just did it. What is the time complexity? Log n per query, right? So we can do that. So in log n time, we were able to make 7 5. Now both of them are at similar level. Why am I doing there? Why am I doing this? Just to simplify the problem, right? Now it is clear. First step 1, we just have to move them to the similar level. How we'll do that? We'll find the difference of level, and whosoever is at the greater level, we will say that, okay, move this, find the, or give me your parent, give me your difference times parents, right? So this is what you will get. So eventually you will be at 4 or 5, right? Now suppose if both of them are equal, which means that this is the LC only, so we'll return that. And if it is not, then we will use the step 2, move A and B to every unequal node and from 16 to 0. Now what are we going to say? Let's say that, okay, or this is a bit difficult to understand, just bear with me. I'll try to take 2 or 3 examples to make this very simple for you guys. All right, so I wrote over here 16 to 0. What are these? These are powers of 2's, right? We will be doing a loop from most significant bit to least significant bit, from 16, 15, and what we will do from 60, if we are at first, okay, so the loop will be from 16 to 0, right? Why we are doing from 16 to 0? You will get to know, don't worry. If we are at 60, we'll say that, okay, what is the 2 to the power 16th parent of 4? Is 0. For 5, again it is 0. So they are at same level, which means if they are at same, if they are same, not at same level, 2 to the power 16th parent of 4 is 0 and 2 to the power 16th parent of 5 is 0, which means they are same. And if they are same, it means that the LCA lies below. LCA lies below. So we don't need to move when they are same. So we'll say that. Now we'll go to 15. 15, again same thing happen, and this same thing will keep on happening till, let's say that, okay, now I is 2 or maybe I is 1. Till 1 till 2 nothing will happen. Now if I is 1, I'll say that, okay, what is 2 to the power 1, which is second parent of 4, we have stored in parent. We'll say that, okay, this is 1. For 5, again it is 1. We won't move again. Now I will go to 0. I will go to 0. Now again, I'll say that, okay, what is the first parent of 4? Again 2. What is the first parent of 5? Again 2. And if they are same, which means that the LCA lies either at that level or below that. Now this loop ended. Now if you see that you will be at, both of the nodes will be at just one level below the LCA, right? Just one level below the LCA. This is just return the first parent, which is already stored, right? So I know it is very like lame to explain in this example. I'll try to give you a bigger picture. Don't worry. Suppose this is the loop. Now these two are the nodes. Suppose I made them on the same level. So 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. Exactly. Now what I will do, I will say that, okay, I is equal to 16. 2 power 16 will be till when they will be having, okay, so this is the LCA. So let me color this in red. This is the LCA, right? Let me color this. Can we do a binary search to find LCA? Binary search. How can you? Okay, let me first explain this thing, then we'll discuss. Then we'll do a brainstorm. Right? Okay, so this, the circular node, the red node is the LCA. The yellow nodes are the nodes A and B, right? Now what I will say that, okay, they are at same level. I brought them on the same level. This is very simple. Now I will do a reverse loop from I equal to 16 to 0. I equal to 16 is basically getting the 2 to the power 16th parent, which is again will be at 0. I will say that, okay, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so let's do a iteration from 3 to 0, because before that 5, 6, 4, everything we will be having 0, right? We will be having same, so we won't move. From I equal to 3, we might have some different nodes, right? So I think that would be like that would save time, and at the same time made you understand. So this is the first parent, second parent, third parent, fourth parent, fifth parent, sixth parent, and for this first parent, second parent, third parent, fourth parent, fifth parent, and sixth parent, and 7, 8, 9, 10, 11, 12, 13, and it is not required, so we'll stop, right? I equal to 3, which means that eighth parent of this is this and this. So do we move forward? Do we move them according to the steps? What does the step says? Move A and B to every unequal node. Are they unequal? No, they are equal, which means that, okay, if they're equal, which means that, okay, the LCA lies below this, right? Below this, which is true. Now we will reduce I. I is 2. What is 2? Fourth parent. What is fourth parent? Are they different? Yes, they are different. So let's move them now. Let's move them. So now, so this will be moved to this, and this will be moved to this. How can you move that? Very simple. We are iterating of powers of 2, just so replace them with dp of node and I, both of them, right? Now you are it over here. 1, I equal to 1. What is 1? 1 basically is 2 power 0, 2 power 1, which is 2. So the second parent for this, now the numbering of parents will change. Let me change that to be very clear. This is 1, 2, 3, 4, and all the parents are same. So I equal to 1 is, which means that, okay, second parent is same, we won't move them, right? Now I equal to 0, the first parent is also same, so we won't move them. And eventually, if you see that, again, we were able to bring these yellow things just one level below the LCA. So what we'll do, just immediate parent of any of the yellow node is the LCA. Now I think it should be clear, or maybe let's take one more example. Should we take one more example, or is it is clear? I won't draw a tree. I won't draw a tree. I just modify this. Or let me draw a tree just to be very clear this time. Delete. Okay. I hope. Okay. Let me draw a tree. Two, three, four, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Suppose these are the yellow nodes. 1, 2, 3, 4, 5, 6, 7, 8. So I equal to through 1, 2, 3, 4, 5, 6. Okay. Let me do. Now I think it should be very clear. All right. Give me a second. All right. So what? Again, we will be doing a loop from 16 to 0. Nothing is significant until we get to I equal to 3. Now I equal to 3, what will be the, let me number the parents. 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Right. I equal to 3 means eighth parent. Eighth parent of both of these is this, which means that whenever the, okay, so whenever the parent is similar, which means that this is the LCA. LCA will always be either at below or at that level, right? It will never be going, it will never be at a greater level, right? That is why we are doing a traversal from I equal to 16 to 0, not 0 to 16, right? The most significant bit to least significant bit is what we are going to do, right? So whenever they are same, I'll say that, okay, either this is the level, or either this is the LCA, or LCA will be below. So if LCA is below, don't move, or even if LCA is over there, don't move, right? Now I equal to 2 is the case. I equal to 2 is the case, which means fourth parent. This is the fourth parent and this is the fourth parent. They are different, which means the LCA is one level up, one level up. So just I'll say that, okay, move, if the LCL is not one level up but is some levels up, then I will say that, okay, just move them to these, because LCA is above and we are moving above, right? So whenever I move this, I'll remove this, right? I'll renumber them. Yeah, I'll renumber them. Now I at I equal to 1, let me renumber them. 1, 2, 3, 4, 5, 5, 4, 3, 2, 1, right? Now I equal to 1, which means that the second parent of this is this, and second parent of this is this. Both of them are different, so I'll again move them. So now this, both of them are different, which means that the LCA is above, so we can propagate them. We propagated them. Now I'll rewrite the number. 1, 2, 3, 1, 2, 3. Now I is at 0, or maybe now it is 0. 0 means immediate parent. Immediate parent are different, so just move them. Just move them. And see what we did. Again, this was the LCA, and we were able to bring both of the yellow dots just one level below the LCA using our algorithm, right? At the end, what we have to do, just return dp of A0 or dp of B0. Both of them will be same. Now is it clear or not? I think it is clear. I took the most complex example that I can take. Everybody left the class. हार्ड हो रहा है क्या? Not clear, Ojas. Okay. Okay. So it is clear. I think I should code then. These are the two simple steps that we will be following. So this was the code for kth parent. I will just write a function, separate function, int get k parent, and int node and int k is what we will be getting. And I won't be taking that. And then what I will do is, okay, I will keep this over here. I will do this. And then I will return node, right? So now the code will be modified. I will be given per query, I will be given int a and b. I'll take a and b and I'll say that I'll first get the level. So I have to get the level. So that is one more problem. No problem. Level of size n plus 1 initialized with 0. While doing the DFS, I will send this thing vector int ampersand level. And one more thing, int L is equal to 0 initialized, right? Over here, I will say that, okay, level of node is L. And whenever I'm doing a DFS, DP level L plus 1. Fine. So in this fashion, we will be able to generate the levels. Levels have been generated. Okay. Level. Fine. I think it is generated now. int A, C in AB. Now both of them are there. So I'll say that, okay, I am assuming that A is at a shorter level and B is at a higher level. And if it is not the case, which means that, okay, if level of A is greater than level of B, I'll swap them. Now at this line, I'm sure that A is at a lesser level, right? So int difference is, I am naming it as K, and level of B minus level of A, and int K is equal to level of B minus level of A. What I will do, I will shift K, I will shift B by K level. So what I will say that, okay, B is equal to get K parent node. What is node? B, and what is K? K only, right? So this is, I am now both A and B are at same level. Just follow the step 2 now. How are we going to follow the step 2? I minus minus. I will say that, okay, if what? If dp of A I is not equal to dp of B I, then move both of them. So A is equal to dp of AI and B is equal to dp of BI. And after this loop end, I was able to show you that the immediate parent of both of them will be the LCA. So C out dp of A 0. In this fashion, I think you will be able to get. So let's see in this test case. In this test case, what are the, let's see what are the LCA of 7 and 6. 7 and 6, and one more, let's say it 2 and no, let's say 6 and 4. So we should be getting some value first of all. Okay, DP is not. Anything else? So LCA of 7 and 6 is 3, which is exactly true, and LCA of 6 and 4 is 1, which is again exactly true. Okay, what if we don't bring them at the same level in the first place? Then you won't be, okay, why are we bringing them on the same level? We want to do a brute force kind of thing. Like we want to So what was the brute force? From initially 7 was B. What was the brute force? Path from 4 to 1. So 4 to 1 is the path from 4 to 1, and path from 7 to 1 is 7, 5, 2, 1. Initially the length are unequal, right? So first of all, we want to make them equal just to start comparing, right? So I just bring them to the same level by bringing them to the same level. 5, 2, 1. Now length is similar. Now I can do that I equal to 16 to 0 stuff, right? So this is the main reason, main motivation behind getting them to the same level. So basically it's like we can get any number by adding some 2 to the power, right? Yes. We have to take yeah. That I forgot to do, right? So every time, if they now A and B are at same level, so just check that if they are equal. If A is equal to B, which means that okay, this is the LCM. So return A. This was to be checked because this only works when both of them are not the LCF, right? So yeah, that is the case. Thanks, Aman. So this is the LCA code. I think it should work again. Let me just run it once more. Fine, it is working. Now got it? Anything? Yes, no? Got it? Clear? Everything clear? Tot till now? All right. Binary search on level will also work, right? Okay, let me think that. How are you going to do a binary search on level? Okay, suppose you are doing a binary search on level, any level mid is there. So what you are going to check in that thing?
Like for example, if we check the mid, that if it is same, then we'll move the L to mid plus one, and then again do that binary search.
Okay.
Like kind of above part, all the parents will be same, right? And then below there will be different. So like it's kind of monotonic.
Monotonic hai, but don't you think that it should? I think it should work, but it will end up taking more time because every time you have to get you are at a level, right? So you will find the first of all you will find the difference of the level from both the nodes. Then you will do what? Find the kth parent of that level,
Yes.
and then again it will, I think, end up taking. You can try doing it yourself. I think it should work. There's nothing wrong in the thinking that the that there is a monotonicity in this function, but it's all yours to try. I haven't tried it. It should work, I think. Like, you can try it on your own, right? Okay. So this is what known as LCA using binary lifting. And remember, this LCA is very important from coding around perspective. A lot of companies, especially Uber, is a fan of giving problems on trees. So just be careful. I remember in my Uber test, I got a tree problem, the third problem, the only problem that I wasn't able to solve. I mean, I was able to solve them partially, but it was a tree problem. It was related to minimum spanning tree, right? And it was a brilliant problem. After that, I never forgot that concept. I think I will be teaching that problem in graphs. Graphs is where we will be learning about spanning trees, right? So then I'll teach you. Anyways, we are left with, let me check what we are left with. LC is done. Now Euler tool is left. Okay. What do you guys want? next class Euler tour in next class or now? Exhausted thoda sa, like the concept was difficult, so I think I should end it now only. Okay, next, everybody next class. Okay, by the way, please send the code. I won't be sending the code. You will get the recording. Try to write it yourself. If you are not able to follow up, just see the recording and write it. Like, see and write. I won't be giving you to just directly use from here, right? So that is one thing that I'm strictly against of. So sorry for that. Oh, thank you to listen me. Anyways, so I think I don't have any feedback form for this class as of now, because I think Priyansh haven't seen the message, but whenever he sees the message, just a request, fill the feedback, right? It is very important for me to get updated with the thing. Like, if I'm doing something wrong, then I'll get to know. Otherwise, it's your loss only, right? So just try filling the feedback form every time, not only in my class, but in every class, right? Anyways, I'll upload these as usual, and then I think we'll meet on Sunday as well for Euler to the next class, right? 28th is when we'll meet. Fine. Okay, Sen. Okay then. Bye to everyone. Enjoy the match.